December 1972 marked the last time a human being stood on the surface of the moon. More than 5 decades have passed since then. In that span, we developed the global internet, decoded the human genome, constructed rockets that land themselves upright, and positioned a telescope 1.5 million kilometers from our planet at a gravitational balance point in deep space. Yet not one person has returned to the lunar surface since Eugene Cernan sealed his hatch and departed. The popular explanation is that we simply moved on. The real explanation is considerably more troubling, far more layered, and far more essential to grasp, because the true reason we have stayed away exposes everything about how our civilization actually functions when confronted with its most demanding undertakings. If you value content that upends conventional thinking and digs into the real story behind the universe's greatest mysteries, please take a second to hit like and subscribe. It means more to this channel than you might realize, and every person who shows support genuinely matters. Make yourself comfortable and settle in. Here we go. There is a single statement that has caused more harm to the public's grasp of space exploration than nearly any other ever uttered. 6 words repeated so casually at kitchen tables, posted so confidently across comment threads, echoed so persistently across so many decades that the claim has hardened into something that passes for truth. We have already been to the moon. Speak it aloud and notice what it assumes. Already. Past tense. Finished. Checked. The phrase treats the moon the way someone might reference a hotel they once visited. Been there. Familiar with the place. Could return whenever. At its most superficial, the statement holds water. Between July 1969 and December 1972, 12 human beings walked the gray surface across 6 successful landing missions. They left behind flags. They gathered 842 pounds of soil and rock. They installed arrays of scientific instruments. They navigated an electric rover across cratered terrain. They captured images that would define an era. Then they came home. What the Apollo program achieved represents one of the most remarkable things our species has ever pulled off. Nobody seriously disputes that it happened or that it mattered profoundly. What deserves to be disputed, what demands scrutiny, is what Apollo actually demonstrated. Because packed inside that offhand sentence is a dangerously misleading premise. The premise is that having gone to the moon one time makes going again a relatively minor logistical exercise. We worked out the engineering. We cracked the fundamental problems. Surely the difficult work is now behind us, and all that remains is gathering the resolve to do it again. That misunderstanding poisons virtually every public discussion about why no human being has set foot on lunar soil in more than 50 years. It treats Apollo as though it were a fixed, enduring capability, a technology we refined, confirmed, and shelved neatly for later retrieval, waiting patiently like a well-tested recipe that just needs someone to follow the steps again. The reality is almost exactly reversed, and grasping why means taking apart everything most people believe about how and why Apollo was achieved in the first place. Strip away the mythology. Forget the stirring addresses and the slow-motion launch footage, and the swelling music behind the documentary narration. Examine Apollo not as a monument to human aspiration, but as the product of extraordinary and specific historical circumstances. When you do, the entire picture shifts. Apollo was not a sustainable program of exploration. It was a sprint, a breathtaking, flawlessly engineered, astronomically expensive sprint conducted under conditions so unusual they may never converge again in the history of our civilization. The program was never intended to open the moon for extended human use. It was designed to land American astronauts safely on the surface and bring them back, within the tightest feasible time frame, at virtually any price, under pressure so overwhelming that ordinary institutional limits were effectively suspended. Understanding why those conditions came about requires traveling back to a single event that rewired America's political priorities in a single night. On October 4th, 1957, the Soviet Union successfully placed a small aluminum sphere into Earth's orbit. Sputnik weighed just 83 kilograms. It carried no armaments. It accomplished no substantive science. It simply circled the globe every 96 minutes, pulsing a radio signal that anyone with a shortwave set could detect. The psychological shock wave this sent through the United States was immense. It is difficult, from today's vantage point, to fully appreciate the intensity of the disruption. America, in the late 1950s, treated its technological supremacy as beyond question. The nation that had conceived and built the atomic bomb industrialized more rapidly than any society in history, and emerged from World War II as the world's preeminent power, had simply assumed that no rival could keep pace with its engineers. Sputnik demolished that assumption in a single evening. The response was not calm or reasoned. It was visceral. Senate hearings opened within weeks. Newspapers ran front-page pieces drawing comparisons to Pearl Harbor. Parents sent worried letters to congressmen asking whether their families were safe under skies now patrolled by Soviet technology. Schools rewrote science curricula almost overnight. A nationwide crisis of self-confidence erupted and reached into every corner of American life. The anxiety was anything but abstract. This was the frozen heart of the Cold War. Both superpowers were constructing nuclear stockpiles at a frightening tempo. The reasoning was stark. If the Soviet Union could orbit a satellite, it could deliver a nuclear warhead to any point on Earth. Sputnik was not a peaceful scientific instrument. It was a demonstration of intercontinental ballistic missile capability, dressed in the language of exploration. Things then grew worse. On April 12, 1961, Soviet cosmonaut Yuri Gagarin became the first human being to orbit the Earth, completing a single loop in 108 minutes before returning safely. The United States, which had yet to achieve orbital spaceflight, could only watch. The strategic stakes were enormous. Across the developing world, nations were aligning themselves with one superpower or the other. Technological capability served as a measure of ideological credibility. Each Soviet achievement in space was a propaganda triumph that rippled across Asia, Africa, and Latin America. The message was blunt and devastating. Communism works. The Soviet model produces results. The future runs through Moscow. It was in this atmosphere, not of scientific enthusiasm but of geopolitical dread, that President John F. Kennedy addressed a joint session of Congress on May 25, 1961. His pledge that America would land a man on the moon and return him safely before the decade closed is remembered today as one of the towering aspirational moments in political history. Less often recalled is the context in which he spoke those words. Kennedy was not fundamentally interested in space. His private correspondence and recorded conversations reveal a leader who viewed the lunar program as a tool. He grasped prestige. He grasped leverage. He understood that the United States was losing ground in its contest for global influence, and needed a demonstration large and unambiguous enough to reverse the tide. The Moon offered that arena. No military project, economic measure, or diplomatic initiative could deliver a single incontrovertible display of technological dominance visible to every nation simultaneously. This distinction is critical. Apollo was not born out of wonder. It was born out of fear. Fear of Soviet supremacy. Fear of ideological retreat. Fear that the arc of the Cold War was curving away from the West. The urgency was the kind that political leaders feel in their bones, not as philosophical abstraction, but as immediate threat to national standing and survival. That urgency translated at once into resources on a scale that has no peacetime American equivalent. At its 1966 peak, NASA absorbed roughly 4.5% of the entire federal budget. Let that sit for a moment. 4.5 cents of every dollar the government spent flowed to the space agency. Adjusted to modern values, that represents approximately $150 billion annually. By contrast, NASA's current yearly budget is roughly $25 billion, well under 0.5% of federal spending. Apollo-era NASA received approximately 6 times more funding in real terms than the agency receives today. And that funding arrived with a speed and political unanimity that bears no resemblance to today's legislative environment. The money was not distributed cautiously. It was deployed at a tempo resembling wartime mobilization, because in nearly every meaningful sense that is exactly what it was. At peak activity, more than 400,000 people worked across approximately 20,000 companies, research institutions, and government facilities. Engineers at Grumman on Long Island built the lunar module, while engineers at North American Aviation in California built the command and service module, while engineers at Boeing in New Orleans built the Saturn V's first stage. Engineers at Douglas Aircraft in California built the third stage, while engineers at IBM built the guidance computers. The supply network spanned every region of the continental United States and concentrated an unprecedented density of engineering expertise. The workplace culture bordered on mania. Weeks of 70 to 80 hours were standard. Engineers slept beside their drawing boards. Families went months without seeing parents consumed entirely by the mission. Test failures that today would initiate multi-year investigation processes were studied, understood, corrected, and overcome in weeks. The scheduling pressure was continuous and deliberate. Kennedy's deadline was not inspirational. It was operational. Every decision, every design trade, every review was weighed against the end-of-decade clock. What emerged from that pressure-driven crucible remains staggering in its boldness. The Saturn V stood 363 feet tall, exceeding the height of the Statue of Liberty on its base. Its 5 first-stage engines together generated 7.5 million pounds of thrust at liftoff, consuming 15 tons of fuel and oxidizer every second. The vehicle could deliver approximately 130 metric tons to low Earth orbit, or roughly 50 metric tons toward the Moon. It remains the most capable launch vehicle ever successfully flown. Nothing that has come since, not the Space Shuttle, not the Falcon Heavy, not the Space Launch System, matches its raw lifting power. Every Saturn V was expendable. The entire vehicle, from the vast first stage down to the compact instrument unit, was used exactly once and then discarded. No reuse, no refurbishment, no thought given to long-term economy. Each launch consumed a vehicle costing approximately $1.5 billion in contemporary dollars. The program flew 13 Saturn V rockets across the Apollo missions, plus additional vehicles for uncrewed testing and Skylab. Each one was a masterwork of engineering intended to fly once and then sink into the ocean or strike the moon. This disposability reveals something essential about Apollo's design logic. The entire architecture was shaped around one objective: deliver crews to the lunar surface and return them home. Not repeatedly, not economically, not sustainably. Once. Demonstrate the capability. Win the contest. Move on. The lunar module embodied this ethos with particular starkness. It was built to sustain 2 astronauts on the surface for roughly 72 hours. It carried oxygen, water, and power, sufficient for that window plus modest emergency reserves. The descent stage held the engine and landing legs that lowered the crew to the surface. The ascent stage held the crew cabin and a single engine that fired them back to lunar orbit for rendezvous with the command module. That ascent engine, the one whose ignition was all that stood between the crew and permanent entombment on the moon, had no backup. No secondary propulsion system. No alternative way to reach orbit. If the engine failed to fire, the crew died on the surface. There was no rescue mission, no contingency vehicle, no alternative plan beyond a pre-drafted presidential address. President Richard Nixon kept exactly such a statement prepared throughout the Apollo 11 mission. Speechwriter William Safire composed remarks titled "In Event of Moon Disaster" that opened with the words that fate had ordained that the men who went to the moon to explore in peace would stay on the moon to rest in peace. That speech was not a formality. It was a genuine contingency for an outcome mission planners considered entirely plausible. The risk tolerance embedded in Apollo is nearly impossible to comprehend from a modern vantage point. Internal NASA estimates from that era placed the probability of crew loss on any individual mission at somewhere between 1 in 20 and 1 in 10, depending on mission phase and specific flight. Some credible analyses placed early mission risk higher still. Across the full program, the cumulative probability that at least one crew would be lost was regarded as substantial. The astronauts understood the odds with precision. They were test pilots, professionals who had spent careers strapping into experimental aircraft with genuine chances of killing them. They embraced the risks not from recklessness, but from a professional culture in which accepting danger was inseparable from the assignment. Many described their relationship with mortal risk in terms that would prompt immediate disqualification in any contemporary crew selection review. And broader American society accepted these risks as well, or at least tolerated them, because the Cold War demanded that tolerance. The perceived cost of losing the space race, of ceding technological leadership to the Soviet Union, was judged greater than the cost of losing astronauts. That calculation was never spelled out so baldly in public, but it governed every budget decision, every schedule call, every design trade that prioritized performance over redundancy. This is the crucial distinction separating Apollo from everything since. The program functioned in a political environment where failure to achieve the objective was deemed more dangerous than failure of the mission itself. That inversion of ordinary institutional values, where the political cost of not attempting exceeded the political cost of crew loss, created conditions under which extraordinary risks were acceptable and extraordinary budgets were justifiable. Eliminate that inversion, and the entire basis of Apollo disappears, which is precisely what occurred. Consider how completely the environment transformed when Space Shuttle Challenger tore apart 73 seconds after liftoff on January 28, 1986, taking all 7 crew members with it. The shuttle fleet sat grounded for 32 months. A presidential commission investigated every aspect of the program. Design modifications were ordered. Launch protocols were overhauled. The institutional wound ran deep and never fully healed. When Space Shuttle Columbia disintegrated during atmospheric re-entry on February 1, 2003, again taking 7 crew members, the fleet was grounded for more than 2 years. The Columbia Accident Investigation Board issued a wide-ranging report examining not only the technical failure, but the organizational culture that had allowed known hazards to become normalized over time. The shuttle program never recovered its footing. It was retired 8 years later. Those responses were the right ones. They reflected a hard-won recognition that human lives cannot be expended casually in the service of programmatic milestones. But they also illustrate why Apollo's operating tempo is structurally impossible in a modern democracy. A single crew loss today would not merely pause a program. It would likely end human deep space exploration for a generation. Congressional inquiries would extend across years. Public trust would collapse. Institutional caution would harden to levels that render ambitious missions impossible to fund. Apollo thrived within a narrow historical window in which a political urgency overrode institutional restraint. That window opened with Sputnik and closed almost the moment Neil Armstrong's boot pressed into the regolith. By the time Apollo 11 succeeded, the political mission was accomplished. The contest was over. The Soviet Union never placed cosmonauts on the moon. American technological superiority had been asserted on history's largest stage. With the political goal met, the political will evaporated almost at once. Cancellations began before the program had even concluded. Missions 18, 19, and 20 were removed from the flight manifest. Not because the hardware wasn't ready. Saturn Verses and lunar modules were already in production at various stages, but because Congress declined to keep paying. Political purpose had been served. The rockets existed. The astronauts were trained. The flights were canceled regardless. That detail is perhaps the most revealing in the entire Apollo story. The United States possessed the physical means to keep flying to the moon and deliberately chose not to use them. The decision was not technical. It was political. The moon had fulfilled its role as a Cold War stage, and no domestic constituency existed that was powerful enough to sustain a program whose founding rationale had been fulfilled. What most people fail to grasp about this history is how thoroughly it reframes the question of lunar return. The common framing runs something like this. We went to the moon 50 years ago, so why can't we simply go back? The implication is that something broke, that we lost capability or nerve or focus. The more precise framing inverts the question entirely. The remarkable thing is not that we stopped going to the moon. The remarkable thing is that we went at all. Apollo was an anomaly, a spike in capability produced by an unrepeatable collision of geopolitical terror, unconstrained budgets, industrial mobilization, and institutional tolerance for mortal risk. The half-century absence of humans from lunar soil is not a failure. It is a return to the baseline reality in which no democratic government possesses sufficient political incentive to spend what it costs to pursue objectives without immediate strategic payoff. This reframing is not meant to diminish Apollo. The program represents one of the supreme achievements in the history of human engineering and courage, but treating it as a baseline, as proof that lunar travel is a solved problem requiring only the will to repeat it, fundamentally misreads what made it achievable. Apollo did not prove that humanity can inhabit the moon. Apollo proved that under conditions of extraordinary political pressure, unconstrained funding, wartime mobilization of industrial capacity, and tolerance for crew risk that would today be considered unconscionable, it is possible to send small groups of remarkably brave individuals on brief visits to the lunar surface and bring most of them back alive. That is a precise achievement, and it is a very different thing from what any modern lunar program requires. Apollo crews did not construct infrastructure. They did not create habitats. They did not evaluate long-duration life support systems, or develop methods of extracting local resources, or build power generation facilities. They landed, conducted surface operations lasting a few hours to 3 days, and departed. The longest, uninterrupted human presence on the lunar surface across the entire Apollo program was approximately 75 hours, during Apollo 17. 3 days on a world that humanity had spent 3 years and roughly 200 billion inflation-adjusted dollars learning to reach. The analogy is imperfect but clarifying. Imagine that in 1969, a team of mountaineers reached the summit of the most treacherous peak on Earth using supplemental oxygen, fixed lines, and a support apparatus involving hundreds of porters and logistics specialists. They planted a flag, took photographs, collected rock samples, and descended. Then imagine that in subsequent decades someone proposed constructing a permanent staffed research facility on that summit, and the public responded by saying, "We've already climbed it. What's the difficulty?" The difficulty is that reaching a destination once under extreme emergency conditions and sustaining a permanent human presence, there are fundamentally different undertakings, separated not by scale but by kind. The capabilities, resources, infrastructure, and institutional commitment needed for the second objective share only superficial overlap with those needed for the first. Apollo was not a platform on which sustained lunar presence could be erected. Apollo was a self-contained event, brilliant and complete, that left behind almost nothing in terms of reusable capability. The Saturn V production lines were not kept open. The lunar module factories were not maintained. The workforce was not retained. The supply chains were not preserved. The institutional knowledge was not handed to a following generation of engineers. When Apollo concluded, it did not leave behind a dormant capability awaiting revival. It left a memory. A magnificent and inspiring memory, but a memory nonetheless. And memories, however vivid, cannot carry astronauts to the moon. The conditions that made Apollo achievable were not simply rare. They were the product of a specific historical moment that combined superpower rivalry, nuclear anxiety, explosive economic expansion, demographic energy, cultural consensus around a national goal, and an appetite for government spending that reflected post-war faith in federal institutions. Each element was necessary. None was sufficient alone. Their simultaneous convergence opened a window of possibility in the early 1960s that began closing the instant Apollo 11 touched down. By 1970, the window had effectively shut. NASA's budget was already shrinking. Public enthusiasm for lunar missions was diminishing. Television audiences for later Apollo flights fell sharply relative to the first landing. Vietnam War expenditures were claiming a growing share of federal resources. Domestic needs in healthcare, education, and urban development competed for funds that Apollo had temporarily monopolized. The Apollo program did not terminate because it failed. It terminated because it succeeded. The political goal was met, and without a political objective of comparable urgency to replace it, the program had no institutional defense against the ordinary pressures of budget competition and priority shifts. This is the heart of the misconception that has distorted public discourse about space exploration for 5 decades. People examine Apollo and conclude that the engineering is proven. What they should conclude is that an exceptional convergence of political, financial, industrial, and cultural conditions can generate results that are inherently non-repeatable once those conditions scatter. Apollo did not construct a highway to the moon. It built a temporary bridge assembled from political necessity and wartime spending, and that bridge was dismantled behind the last departing astronaut. What was lost during that dismantling is far more than most people recognize. That story begins with the factories that fell silent and the engineers who dispersed. Most observers assume that, after Apollo, NASA simply redirected its energies. The shuttle gained priority. Low Earth orbit became the new arena. The moon was held in reserve, deferred rather than abandoned. The assumption is that the capability to return sat quietly waiting, like a classic vehicle under a tarp, needing only someone to turn the key. This assumption is wrong in ways that are hard to fully convey. What followed Apollo was not a redirection. It was a demolition. Start with the most tangible loss, the Saturn V. The Saturn V was not preserved as an operational system. It was not placed in storage with maintenance crews keeping it viable until political winds shifted. Production lines were closed down. The specialized tooling, jigs, welding rigs, calibration fixtures, and custom forming dies were dismantled and in many cases destroyed. The factories that had produced the F-1 engines, each one a masterwork of precision engineering channeling liquid oxygen and kerosene through thousands of individual injector orifices to generate 1.5 million pounds of thrust, were retooled for entirely different purposes or shut down entirely. Contractors who had built the Saturn V's major components received no continuation orders. North American Rockwell, builder of the S-2 second stage, moved on to defense contracts. Douglas Aircraft, builder of the S-4B third stage, was absorbed into McDonnell Douglas and eventually Boeing. The Michoud assembly facility in New Orleans, where first-stage propellant tanks were welded inside a building so vast it generates its own internal weather, was repurposed for space shuttle external tank production. The physical infrastructure persisted, but its configuration, workforce, and institutional purpose had been completely transformed. 3 unused Saturn V rockets survived. One rests horizontally at Kennedy Space Center in Florida. Another stands upright at Johnson Space Center in Houston. A third is exhibited at the U.S. Space and Rocket Center in Huntsville, Alabama. They are magnificent artifacts, and artifacts is exactly the right word. They are objects preserved for contemplation, not for operation. You cannot fuel a museum exhibit. You cannot launch a display piece. And even if you could, a single rocket is not a space program. A space program is a living system of factories, supply networks, engineering teams, test facilities, launch infrastructure, and institutional knowledge functioning as an integrated organism. The rockets in those museums are organs removed from a body that no longer exists. The loss of the Saturn V, striking as it is, represents only the most visible element of a far deeper destruction. The true devastation was not the hardware. It was the human infrastructure that created it. At its peak, the Apollo workforce reached across every state, employing 250,000 engineers and technicians, supported by a still larger network of manufacturing and logistics workers. These were not interchangeable laborers, performing standard tasks. They were specialists, welders who understood the precise metallurgical behavior of aluminum-copper alloys used in cryogenic tanks at temperatures reaching minus 250 degrees Fahrenheit. Machinists who could hold tolerances of 10,000ths of an inch on turbopump components, spinning at 6,000 revolutions per minute. Electrical engineers who designed wire harnesses containing miles of cabling required to survive the acoustic shock and thermal punishment of launch. Systems engineers who understood how 10,000 subsystems drawn from 200 suppliers integrated into a single vehicle that had to perform flawlessly on every flight with human lives at stake. When Apollo ended, these people did not pause indefinitely. They moved on. Welders found positions in shipyards and petrochemical plants. Machinists transferred to automotive and defense manufacturing. Electrical engineers joined the nascent computing industry. Systems engineers scattered across a dozen sectors. Within 5 years of the final lunar mission, the workforce that had made Apollo possible was dispersed throughout the American economy. Its collective expertise diluted past recovery. Some of this expertise had been captured in documents. Blueprints existed. Technical reports filled warehouses. Test data had been archived on magnetic tape and microfilm. But anyone who has attempted to reconstruct something complex from documentation alone understands the gulf between what drawings show and what experienced hands know. A blueprint can specify a weld joint's geometry, filler material, current and voltage settings, and shielding gas composition. What a blueprint cannot capture is the intuitive adjustment a seasoned welder makes to compensate for the way a specific alloy warps under thermal stress across a multi-pass cryogenic tank seam. That modification, a slight torch angle change, a travel speed absorbed through years of practice, an instinct for when the weld pool is behaving correctly, exists as tacit knowledge. It lives in muscle memory and professional intuition. It is transmitted not through documents but through direct mentorship, through standing beside someone who has done it 10,000 times and absorbing what cannot be written. When the Apollo workforce scattered, those chains of transmission broke. The masters departed and took their mastery with them. The apprentices who might have carried that knowledge forward were never trained because there was no program for which they could be trained. NASA discovered the true depth of this loss decades later, and the discovery was disquieting. During the 1990s, engineers at Marshall Space Flight Center, attempting to consult Saturn V documentation for new rocket development, found an archive far less useful than anyone had imagined. Blueprints were incomplete. Manufacturing specifications referenced procedures identified only by internal designation codes that no surviving engineer could interpret. Assembly instructions contained notes like "per standard shop practice," a phrase transparent to the technicians of 1966 and entirely opaque to anyone reading it 3 decades later. The standard shop practice had walked out the door with the people who once performed it. Some accounts describe this situation with the phrase, "we lost the technology." That formulation, emotionally resonant and widely repeated, is slightly imprecise in a way that matters. The underlying physics did not change. Newton's laws still govern rocket propulsion. The thermodynamic principles of combustion chamber design remain fully understood. The foundational engineering knowledge that enables rocket construction has not been forgotten. What was lost was something more specific and, in practical terms, more catastrophic: the industrial capacity to manufacture the particular hardware. The supply chains that delivered exotic alloys in required grades and volumes. The manufacturing processes refined across years of trial and error. The quality control protocols calibrated to the singular demands of human-rated spaceflight hardware. The integration expertise enabling components from hundreds of sources to combine into a functioning vehicle. The institutional reflexes, knowing which anomalies were serious and which were benign, knowing when to stop analyzing and start building, knowing how to navigate the 1,000 small decisions per day that a complex program demands. Rebuilding this capability is not a matter of retrieving old drawings and handing them to a modern shop. It requires reconstituting an entire ecosystem of specialized production in an industrial landscape that has been transformed beyond recognition since the 1960s. Consider one modest example. The injector plate for the F-1 engine contained roughly 2,600 individual fuel and oxidizer orifices, each precision-drilled and positioned to create a spray pattern, ensuring stable combustion at chamber pressures approaching 1,000 pounds per square inch. Manufacturing this single component required specialized drilling equipment, custom fixtures, and a quality inspection regimen spanning weeks per unit. The technicians who produced them developed intuitive knowledge of how drill wear affected hole geometry, how fixture alignment shifted across production runs, and how to detect dimensional deviations that could trigger combustion instability. When NASA engineers revisited F-1 documentation decades later as part of studies into next-generation propulsion development, they found that recreating the injector plate using modern methods was straightforward in principle, but surprisingly arduous in practice. The original specifications assumed manufacturing approaches that no longer existed. Modern CNC machining could achieve the required tolerances, but process parameters had to be built from scratch. The tacit knowledge of how original injectors were validated, which test signatures were acceptable, which anomalies could be tolerated, which data patterns flagged emerging problems, had to be painstakingly reconstructed through expensive, time-consuming iteration. Multiply that challenge across every significant component of a heavy-lift launch vehicle, and you begin to appreciate the true scale of what was forfeited. The Saturn V contained roughly 3 million individual parts, each manufactured, inspected, and integrated by people whose expertise vanished with the program. Rebuilding the capacity to produce even a fraction of those components demands investments in time, money, and human capital that exceed the cost of the original development, because that original development benefited from a fully operational industrial base that no longer exists. The budget trajectory that followed Apollo's conclusion ensured that no such rebuilding would occur for decades. Following the apex of the Apollo funding era, NASA's budget entered a long descent that never reversed. By 1970, the year after the first lunar landing, NASA's budget had already contracted substantially. By 1975, it had fallen to roughly 1% of federal spending. It has since fluctuated in a range between 0.5% and 1%, rising and falling with political conditions, but never approaching anything resembling Apollo-era investment. That funding level is not negligible. 1% of the federal budget still represents many billions of dollars annually, but it is fundamentally inadequate to simultaneously sustain existing programs and develop new deep space capabilities. For 50 years, NASA has been compelled to make trade-offs that Apollo-era leadership never faced. Which priorities to fund and which to postpone, which technologies to advance and which to shelve, which missions to fly and which to leave on drawing boards. The Space Shuttle absorbed the consequences of that constrained budget more completely than any other program, and in doing so, consumed the resources that might otherwise have sustained or reconstructed deep space capability. The shuttle was pitched to Congress and the American public in the early 1970s as a transformation in space access. The case was appealing. A reusable spacecraft that would launch like a rocket, function in orbit as a laboratory, and land on a runway like an aircraft. Flight rates of 40 to 50 missions per year, per-flight costs low enough to make space routine. A vehicle versatile enough to serve military, scientific, and commercial clients simultaneously, rendering the costly, expendable rockets of the Apollo era obsolete. Virtually none of those promises came true. The shuttle flew 135 missions across 30 years of operation, averaging roughly 4.5 flights annually, not 50. Each mission cost approximately $1.5 billion when all operational and infrastructure expenses were included. Turnaround time between flights stretched to months rather than weeks. The vehicle required an enormous workforce of technicians to inspect, refurbish, and recertify between missions. Reusability, which was meant to compress costs, instead increased them because of the extraordinary maintenance burden imposed by repeated exposure to the thermal and mechanical violence of launch and re-entry. The shuttle was not a poor spacecraft. In many respects, it was a genuinely extraordinary piece of engineering. It could haul payloads of up to roughly 23 metric tons to low Earth orbit. It carried crews of up to 7. It made construction of the International Space Station possible, delivering modules and components that no other vehicle of its era could have transported. It deployed, serviced, and repaired the Hubble Space Telescope. It conducted hundreds of experiments spanning disciplines from materials science to human physiology. But the shuttle had a hard ceiling, and that ceiling was low Earth orbit. Maximum operational altitude was approximately 600 kilometers. The Moon lies 384,000 kilometers away. The shuttle was no more capable of reaching the Moon than a harbor ferry is capable of crossing an ocean. Yet, for 3 decades, this orbital vehicle absorbed the overwhelming majority of NASA's human spaceflight budget, workforce, facilities, engineering attention, institutional priority, and political capital. This is not primarily a critique of the shuttle's design or the people who operated it. It is a structural observation about what happens when a single program monopolizes a constrained budget. Every dollar spent sustaining shuttle operations was a dollar not invested in next-generation deep space transportation. Every engineer stationed on shuttle maintenance was an engineer not designing heavy-lift launch vehicles, lunar landers, or deep space habitats. Every management decision oriented around shuttle flight rates and safety requirements was a decision that did not advance the challenge of returning humans to the Moon. Consider what 3 decades of constrained budgets genuinely prevented. Throughout the 1980s and 1990s, while shuttle operations consumed the bulk of NASA's human spaceflight resources, an entire generation of deep space technologies remained undeveloped. Lunar lander concepts existed only on paper. Closed-loop life support systems capable of sustaining crews for weeks beyond low Earth orbit received modest laboratory funding rather than the flight development investment needed to produce operational hardware. Advanced spacesuit designs capable of managing abrasive lunar dust progressed through conceptual studies without ever reaching the prototype phase. In situ resource utilization, the technology that could one day enable astronauts to extract water and manufacture propellant from lunar regolith, remained a theoretical framework discussed at scientific conferences. Deep space habitation modules, radiation-hardened power systems, autonomous surface rovers suited to the lunar thermal environment. Each represented a technology requiring a decade or more of sustained development to reach flight readiness. Each received intermittent study funding that produced reports and position papers, but no flight hardware. The shuttle did not merely prevent NASA from flying to the moon. It prevented the agency from developing the technologies that would have compressed the timeline for any future lunar program when the political moment eventually arrived. Every year that elapsed without consistent investment in those capabilities was a year added to the eventual return. The opportunity cost was staggering. Across 30 years of shuttle operations, NASA spent approximately $200 billion in inflation-adjusted terms. That figure is comparable to the full cost of Apollo. Except Apollo produced a capability to reach the moon, while the shuttle produced a capability to reach an altitude roughly 1,000th of the way there. The International Space Station extended and intensified this pattern. Construction began with the first module launch in 1998 and consumed enormous resources across the following decade. The station is a genuine wonder of international engineering. It has maintained an unbroken scientific research platform in orbit for more than 2 decades. It has generated invaluable data on the physiological effects of prolonged microgravity, data essential to any future deep space mission, including lunar return. But like the shuttle that built it, the station occupies low Earth orbit, and like the shuttle, it consumed budget, engineering bandwidth, and institutional attention that might otherwise have been directed toward deep space capability development. For roughly 2 decades, NASA's human spaceflight program was defined by 2 objectives almost exclusively: operating the shuttle and building and maintaining the station. Both were worthwhile undertakings. Neither moved a single human being 1 kilometer closer to the moon. The combined effect of shuttle and station dominance was a half-century absence of any deep space human exploration capability. When the final Apollo crew left the lunar surface in December 1972, the United States possessed operational hardware capable of delivering humans to the moon. By the time the shuttle retired in July 2011, that capability had been absent for nearly 4 decades, and the industrial foundation required to recreate it had been utterly transformed. Several attempts were made to escape this cycle, and understanding why they fell short reveals the structural nature of the problem. In 1989, marking the 20th anniversary of the Apollo 11 landing, President George H.W. Bush announced the Space Exploration Initiative from the steps of the National Air and Space Museum. He called for a permanent lunar return and eventual crewed missions to Mars. NASA responded with what became known as the 90-day report, which outlined an architecture estimated to require $500 billion across 20 to 30 years. Congress recoiled at the cost. The initiative was functionally extinct within 2 years, killed not by technical impossibility, but by fiscal unwillingness. In 2004, President George W. Bush announced the vision for space exploration, calling for completing the International Space Station, retiring the shuttle, developing new crew and cargo vehicles, and returning astronauts to the Moon by 2020. The resulting Constellation program produced early designs for the Ares 1 crew launch vehicle, the Ares 5 heavy-lift cargo rocket, the Orion crew capsule, and the Altair lunar lander. Real engineering proceeded. Metal was machined. Tests were run. Progress materialized. But the program was chronically underfunded relative to its ambitions. Schedules slipped. Costs climbed. The Augustine Commission, convened by President Obama in 2009 to evaluate NASA's human spaceflight direction, concluded that Constellation's objectives were not achievable under projected budget profiles. Without substantial budget increases neither the administration nor Congress was prepared to provide, the program could not achieve a lunar landing within any credible timeframe. In 2010, President Obama canceled Constellation. The Ares 1 and Altair lander were terminated. The Ares 5 evolved into what eventually became the Space Launch System. The Orion capsule survived and continues development as part of the Artemis architecture. But billions in development expenditure on canceled systems yielded no operational hardware. Engineers who had devoted years to Constellation-specific components watched their work archived rather than flown. The human cost of that cancellation extended far beyond wasted dollars. Engineers who had relocated families to Huntsville, Houston, or the Cape in expectation of building next-generation deep space vehicles found themselves reassigned to programs of uncertain longevity or laid off entirely. Mid-career specialists who had spent 5 or 6 years building expertise in Constellation-specific technologies, the Altair lander throttleable descent engine, the Ares 5 Earth departure stage, the surface habitat thermal protection architecture, found their skills had no immediate application anywhere else. Some pivoted toward the nascent commercial space sector. Others departed aerospace entirely, carrying with them precisely the deep space engineering experience that would be critically needed when the next lunar program inevitably materialized. The institutional erosion compounded with each iteration. By the time Artemis was announced, an entire generation of aerospace professionals had been formed entirely by programs that started and stopped. Their professional formation had not involved building and flying hardware. It had involved designing systems that were terminated before reaching the pad. This created a characteristic kind of institutional caution, a reluctance to invest fully in any program's long-term trajectory, because career experience had taught that trajectories change with each new administration. Recruiting the next generation of engineers became increasingly difficult when the most accurate answer to, "Will this program exist in 10 years?" was an uncomfortable silence. In 2017, the Trump administration signed Space Policy Directive 1, reorienting NASA toward the Moon. By 2019, the timeline had been compressed to target a crewed landing by 2024. The Artemis program was formally constituted, built around surviving Constellation elements, primarily Orion and SLS, while incorporating new components including the Lunar Gateway and commercially developed human landing systems. The program represented the most concrete and best-funded attempt at lunar return since Apollo itself. But even Artemis has struggled against the structural forces that toppled its predecessors. The Space Launch System, though technically formidable, has faced persistent cost growth and schedule expansion. Its per-flight cost, estimated at over $4, billion for early missions by NASA's own Inspector General has drawn criticism from proponents of commercial alternatives. The human landing system development, contracted to SpaceX and later also to Blue Origin, depends on technologies, particularly orbital propellant transfer at scale, that have never been demonstrated operationally. Timelines have slipped repeatedly. The original 2024 landing target was deferred to 2025, then to 2026, and may move further. Each of these programs, the Space Exploration Initiative, Constellation, and to a meaningful degree Artemis, has collided with the same fundamental barrier. Not engineering impossibility, but the mismatch between the timescales of space hardware development and the timescales of political commitment. Developing a new human-rated launch vehicle from concept to operational flight takes approximately 10 to 15 years under favorable conditions. Adding a lunar lander, a deep space habitat, and the associated ground infrastructure extends the timeline further. A credible projection for establishing sustained lunar surface capability starting from the post-shuttle baseline spans decades rather than years. No American president serves more than 8 years. Congressional priorities shift with every election cycle. Federal budgets are authorized annually with limited capacity to obligate future Congresses to multi-year spending commitments. A program requiring decades of consistent investment must survive multiple presidential transitions, each bringing new priorities, new advisors, and new calculations about discretionary spending allocation. The outcome has been a cycle of initiation and abandonment, consuming tens of billions of dollars while producing remarkably little operational deep space capability. Each new administration declares ambitious goals. Each funds a program that makes genuine but incomplete progress. Each successor examines the inherited program, judges it too costly, too slow, or misaligned with updated priorities, and restructures or cancels it. Engineers who devoted years to one architecture watch it dissolved and are asked to begin fresh on a replacement. Industrial partners who invested in specific technologies see contracts canceled and production lines idled. Institutional knowledge built during one program's development is partially lost in the transition to the next. This is not merely inefficient, it is actively corrosive. Each cancellation does not simply fail to advance the objective. It sets the effort back by disbanding teams, forfeiting invested capital, and eroding the confidence of the workforce and industrial base that any future program will survive long enough to be completed. The aerospace industry has learned to receive lunar return announcements with a particular variety of tired skepticism. Engineers who joined NASA or its contractors in the early 2000s to work on Constellation watched that program terminated. Some were reassigned to SLS and Orion development, only to watch timelines extend and budgets tighten. Younger engineers entering the field today carry no institutional memory of a time when deep space human exploration programs reached completion. Their entire professional formation has been shaped by programs that begin, struggle, and stop. This workforce erosion may be the most durable damage inflicted by the post-Apollo decades. Rockets can be designed relatively quickly. Factories can be constructed in a few years, but cultivating a workforce with the skills, accumulated experience, and institutional confidence to execute something as intricate as lunar return demands a full generation. That generation must be recruited, trained, retained through the inevitable difficulties of development, and given the opportunity not only to design hardware, but to see it built and flown. The start-stop cycle denies them that experience, and in doing so, it undermines the very foundation on which any future program must stand. The cumulative picture, 53 years after the last human footprint was pressed into lunar soil, is sobering. The rockets are gone. The factories have been repurposed. The workforce has dispersed. The institutional knowledge is fragmented. The budget is a fraction of what Apollo required. Multiple attempts to rebuild deep space capability have been launched and abandoned, each consuming resources while leaving behind only partial progress and institutional scar tissue. The contemporary effort to return humans to the moon does not depart from where Apollo left off. It departs from a starting position that is in many practical respects more challenging than where Apollo itself began, because Apollo began from a blank page and an effectively unlimited budget. Artemis must navigate the accumulated technical debt, political history, and institutional damage of 5 decades of false starts. The contrast between Apollo's industrial context and today's reaches even into the basic mechanics of procurement and manufacturing. In the 1960s, NASA could direct contracts to specific companies through relatively streamlined processes. The agency could enforce domestic sourcing for virtually every component, ensuring supply chains remained within national borders under direct governmental monitoring. Manufacturing facilities were frequently purpose-built with federal funds specifically for Apollo hardware, meaning the agency effectively controlled production capacity. Modern aerospace procurement operates through dense layers of regulatory compliance, competitive bidding requirements, intellectual property negotiations, and international trade considerations that add years and significant cost to every major contract. Supply chains are globally distributed. A single rocket engine may incorporate alloys sourced across 3 continents, electronic components fabricated in multiple countries, and software produced by teams spanning half a dozen time zones. Managing this complexity is achievable, but it imposes overhead costs and schedule risks that Apollo's domestically concentrated industrial base simply never confronted. The industrial machine that sent humans to the moon was not mothballed. It was not preserved. It was dismantled part by part, person by person, decision by decision, until nothing remained but museum installations and fading documentation. Rebuilding it, or rather constructing an entirely new one suited to contemporary requirements, is the defining challenge of this era. And that challenge is made enormously harder by a fact most people find counterintuitive. The mission itself, the actual work of placing humans on the moon and keeping them alive, is more demanding today than it was in 1969. Not because the moon has changed, because everything we now require of the mission has changed beyond recognition. That transformation is where the story turns next. There is a deeply intuitive assumption that shapes how most people conceptualize technological progress. It runs roughly like this. If we could accomplish something 50 years ago with rudimentary tools, we should be able to accomplish it better, faster, and more cheaply today with modern capabilities. The phones we carry contain more computing power than every machine used throughout the entire Apollo program combined. We have materials science the 1960s could not have conceived. We possess manufacturing precision, computational modeling, communication bandwidth, and simulation capabilities that would have read as science fiction to the engineers who designed the Saturn V. Surely, with all of that, reaching the moon should be simpler now than then. The reasoning feels airtight. it is also fundamentally mistaken. Not because the technological gains are illusory, they are genuine and meaningful, but because they are being applied to a categorically different problem. The mission Apollo was designed to execute, and the mission modern lunar programs must execute, share a destination. They share almost nothing else. Grasping that distinction is essential to understanding why returning to the moon has taken so long, and why the engineering challenge is in several critical dimensions harder today than it was in 1969. The difficulty does not arise from the moon itself, which has not changed. It arises from what we now require of any mission carrying human beings beyond low Earth orbit. Begin with the most fundamental architectural difference, because it determines everything downstream. Apollo was structured around a single governing principle: minimum exposure time. Reach the surface, conduct activities, depart the surface, return home. Every element of the mission profile was engineered to minimize the duration of exposure to every hazard the lunar environment presents. Crews spent between 21 and 75 hours on the surface across the 6 landing missions. The longest surface stay during Apollo 17 lasted just over 3 days. Transit time between Earth and lunar orbit consumed approximately 3 days each direction. Total mission duration from launch to splashdown ranged from 8 to 12 days. Every system aboard the spacecraft was sized for that window and nothing beyond it. Oxygen reserves, water supplies, food, carbon dioxide absorption capacity, battery charge, thermal regulation, each was calculated against the expected mission duration, plus a modest emergency margin. There was no surplus. No provision for extending the stay if something remarkable was discovered. No ability to wait through an emergency lasting longer than the onboard reserves could support. This was not inadequate planning. It was radical optimization. Every additional kilogram of consumables meant 1 fewer kilogram of something else: scientific instruments, propellant reserves, structural margin. The lunar module was mass-constrained to such a degree that its pressure vessel walls measured barely 1/3 of a millimeter thick in certain sections, thin enough that a technician pressing too firmly during assembly could risk puncturing the vessel that kept the crew alive. Every gram was agonized over, because the mission was designed to require as few grams as possible. Modern lunar programs cannot operate within those constraints. The objectives have shifted fundamentally. Artemis and its international counterparts are not designed to plant flags and collect samples on brief expeditions. They are designed to establish sustained human presence, missions initially spanning weeks, then months, then eventually permanent habitation with rotating crews. The architectural requirements for that kind of sustained presence are categorically different from what Apollo demanded, and the differences multiply across every system and subsystem on the vehicle and on the surface. Consider life support, because it illustrates the scaling problem with particular sharpness. Apollo relied on what engineers term open-loop life support. Oxygen was stored under pressure and released into the cabin as consumed. Carbon dioxide exhaled by the crew was removed by routing cabin air through lithium hydroxide canisters, chemical beds that absorbed carbon dioxide through an irreversible reaction. Once saturated, a canister was discarded and replaced. Water was produced as a byproduct of the hydrogen-oxygen fuel cells supplying electrical power. Food was prepackaged. Waste was collected and stored. This approach functions elegantly for brief missions. Consumable mass scales directly with crew size and duration. 2 astronauts for 3 days requires a defined quantity of oxygen, lithium hydroxide canisters, water, and food. The numbers are manageable. The systems are uncomplicated. Failure modes are well characterized. The entire life support architecture for an Apollo lunar module surface stay weighed a few hundred kilograms. Now, apply that same open-loop framework to a 28-day mission with a crew of 4. Oxygen demand increases roughly 19-fold. Lithium hydroxide canister requirements multiply by the same factor. Water consumption, encompassing not only drinking but food preparation, equipment cooling, and hygiene, scales proportionally. Food mass expands. Waste storage volume grows. The total consumable mass for a 4-week surface mission using Apollo-style open-loop life support would substantially exceed the entire payload capacity of the lunar module. You cannot provision a month-long stay with systems designed for a 3-day excursion. The solution involves partially or fully closed-loop life support that recycles air and water rather than consuming and discarding them. The International Space Station has operated such systems for over 2 decades, and they function. The station's water recovery system processes humidity, condensate, and urine into potable water, with recent upgrades including a brine processor assembly, pushing recovery efficiency to approximately 98%. The oxygen generation system electrolyzes water to produce breathable oxygen. The carbon dioxide removal assembly employs regenerable sorbent beds reusable thousands of times rather than disposable canisters. These systems dramatically reduce the consumable mass that must be launched from Earth. Rather than carrying all the water a crew will need for an entire mission, you carry a modest initial supply and recycle it continuously. Rather than packing hundreds of canisters, you install a regenerable system that processes carbon dioxide indefinitely with only periodic maintenance. But closed-loop life support introduces complexity that open-loop systems avoid entirely. The water recovery system aboard the International Space Station is a sophisticated chemical engineering assembly incorporating distillation, filtration, catalytic oxidation, and ion exchange processes. It requires regular maintenance, filter, and catalyst bed replacement, and ongoing monitoring by trained crew members. It has experienced failures, pump seizures, contamination events, sensor malfunctions demanding troubleshooting and repair during active operations. Those failures are manageable in orbit because resupply vehicles can deliver replacement components within weeks, and crews can subsist on stored reserves while repairs proceed. On the lunar surface, the arithmetic changes completely. Resupply from Earth requires a dedicated launch, transit, and landing, a process measured in weeks into months, not days. Spare components must either be carried from Earth in advance, adding mass and cost, or fabricated locally using capabilities that do not yet exist. A life support failure that would be a minor operational interruption on the station becomes a potential crew emergency on the Moon. This reality demands redundancy, backup systems, spare component inventories, alternative operating configurations, each adding mass, complexity, and cost. Adapting station-derived life support technology for the lunar environment introduces additional challenges with no equivalent in low Earth orbit. Lunar gravity is roughly 1/6 of Earth's. Fluid systems relying on gravity-driven separation, which encompasses many water recovery processes, must be redesigned for the reduced gravitational field. Lunar dust, which infiltrates virtually every exposed system it contacts, creates contamination risks for filters, seals, and fluid handling components. The thermal environment on the lunar surface, swinging from roughly 120 degrees Celsius in sunlight to minus 170 in shadow, imposes thermal management demands that the station's comparatively stable orbital environment never generates. None of these problems lack solutions. Engineers have proposed and, in some cases, prototyped approaches to each. But each solution requires development, testing, qualification, and integration processes consuming years and billions of dollars. Life support systems for sustained lunar presence represent not a modest evolution from Apollo, but an entirely different technological generation, more closely related to what will ultimately be required for Mars missions than to anything that flew in the 1960s. Radiation protection presents an equally sharp contrast between the Apollo approach and contemporary requirements, and the difference is governed entirely by duration. The Moon possesses no global magnetic field. It has essentially no atmosphere. Its surface is exposed without any meaningful attenuation to the full range of space radiation. This encompasses galactic cosmic rays, high-energy particles originating from supernovae and other violent astrophysical processes throughout the galaxy, and solar particle events, intense surges of energetic protons ejected by the Sun during coronal mass ejections and solar flares. Galactic cosmic rays deliver a slow, continuous radiation dose that accumulates with time. Individual particles carry extraordinary kinetic energy. Some carry the energy of a professionally thrown baseball concentrated in a single atomic nucleus. These particles penetrate conventional shielding materials, and some produce secondary radiation cascades when they interact with shielding material, potentially increasing the dose received by crew members behind thin shields rather than reducing it. Effective shielding against galactic cosmic rays requires substantial mass. Meters of regolith, or thick layers of hydrogen-rich materials such as polyethylene or water. Solar particle events differ in character, but can be more immediately dangerous. A major solar event can deliver within hours a radiation dose that would otherwise accumulate over months of galactic cosmic ray exposure. Event intensity is unpredictable. Warning time can be very short, sometimes as little as 15 to 30 minutes, between the first detectable solar signatures and the arrival of energetic particles at lunar distance. Duration can range from hours to days. The most severe events on record would expose unshielded astronauts on the lunar surface to doses capable of inducing acute radiation sickness, suppressing immune function, and potentially causing death. Apollo crews faced these hazards. They survived because their missions were short and because fortune favored them. None of the Apollo surface stays coincided with a significant solar particle event. That was not a guarantee. Solar activity during the Apollo era was moderate, but notable events did occur between missions. A major proton event in August 1972 fell between the Apollo 16 and Apollo 17 flights. Had it occurred during a surface stay, crew members would have received an estimated dose of several hundred millisieverts within hours, sufficient to produce acute symptoms and substantially elevate lifetime cancer risk. Whether it would have been lethal is contested, but it would unquestionably have constituted a medical emergency without any treatment available on the surface. For a 3-day visit, accepting that risk was a calculated wager, consistent with Apollo's broader approach to crew safety. The probability of a significant event occurring during any specific 72-hour window is low. Across a limited number of missions, The cumulative probability remains manageable if you are willing to absorb the consequence when the wager fails. For missions lasting weeks or months, the calculation transforms entirely. Galactic cosmic ray exposure grows linearly with time. A 30-day surface stay delivers roughly 10 times the galactic cosmic ray dose of a 3-day stay. Over months, accumulated dose approaches or exceeds career radiation limits established by contemporary spaceflight medicine. And the probability of experiencing at least one significant solar particle event during an extended surface mission grows substantially. For a mission spanning a full lunar cycle of 29.5 Earth days, the probability is no longer a marginal risk. It becomes a near certainty over multiple mission rotations. Modern mission architectures must therefore embed radiation protection as a foundational design requirement rather than an accepted probability. This means surface habitats shielded sufficiently to reduce galactic cosmic ray exposure to tolerable levels, likely through regolith piled over habitat structures to several meters depth, or through siting within lava tubes that provide natural overhead cover. It means dedicated radiation storm shelters within every pressurized volume, capable of protecting crew members during solar particle events, stocked with sufficient provisions for stays of 24 to 72 hours. It means real-time radiation monitoring and early warning capabilities linked to solar observation networks with continuous coverage. Each requirement adds mass, cost, and complexity. A habitat designed for regolith burial must have structural integrity sufficient to support the overburden. A storm shelter must be accessible from every surface worksite within available warning time. Monitoring and warning systems must be reliable and redundant. None of this existed in the Apollo architecture because none of it was needed for a 3-day sprint. The lunar surface thermal environment imposes engineering demands that Apollo successfully avoided through timing, but which sustained presence cannot escape. The Moon completes one rotation every 29.5 Earth days, producing approximately 14 days of continuous sunlight, followed by 14 days of continuous darkness at most surface locations. During the sunlit period, surface temperatures at equatorial latitudes reach approximately 120 degrees Celsius. During the lunar night, temperatures plunge to approximately minus 170. The transition is abrupt. Because the Moon has no atmosphere to redistribute or retain heat, temperatures shift rapidly as the sun rises or sets at the local horizon. Apollo missions landed during lunar morning at carefully selected equatorial sites, ensuring moderate thermal conditions throughout each surface stay. Crews were never present long enough for thermal conditions to shift meaningfully. The lunar module's thermal control system was designed for a narrow operational temperature range and short operational duration. It was never exposed to the extremes of the full day-night cycle because it was never present for them. Sustained presence must operate across both extremes. Equipment must function at temperatures that would solidify carbon dioxide during the night and approach the boiling point of water by day. Materials expand and contract through thermal cycles that impose stress on joints, seals, and structural connections. Electronics must either be actively maintained above minimum operating temperature during the night or engineered to survive repeated thermal cycling without failure. Lubricants in mechanical systems must perform across a nearly 300 degrees Celsius range. Power generation is the most immediately consequential thermal challenge. Solar arrays generate abundant electricity during the 14-day sunlit period, but produce nothing during the equally long night. For a sustained surface outpost, this means either storing enough energy during the day to power all operations through 2 weeks of darkness, requiring battery capacity, many orders of magnitude beyond current technology, or deploying nuclear power sources that operate independently of solar illumination. NASA and the Department of Energy have been developing fission power systems for the lunar surface, progressing from the kilopower technology demonstration toward the fission surface power project, targeting approximately 40 kilowatts of continuous electrical output per unit. This is a meaningful starting point, but a functional outpost with operating life support, thermal control, science activities, and in situ resource processing will require substantially more. Multiple units will be needed, along with the infrastructure to deploy, interconnect, and maintain them. Artemis has partially addressed the thermal and power challenges by concentrating initial landing activities near the lunar South Pole. Certain elevated terrain near the South Pole receives near-continuous sunlight because of the Moon's minimal axial tilt of just 1.5 degrees from the ecliptic plane. These so-called peaks of eternal light offer dramatically more favorable thermal and power conditions than equatorial terrain. Solar arrays positioned on these elevations could generate power nearly continuously, with only brief interruptions during shadow periods. But even these favorable sites sit adjacent to some of the most extreme thermal environments in the solar system. Permanently shadowed craters near the lunar poles, regions that have not been touched by sunlight across billions of years, harbor temperatures as low as minus 230 degrees Celsius, colder than the surface of Pluto. These craters hold enormous scientific and operational significance because they are believed to contain water ice deposits accumulated over geological timescales through cometary bombardment and solar wind implantation. That water ice may represent the single most strategically valuable resource available for sustained lunar presence. If it can be extracted and processed, it yields drinking water, breathable oxygen through electrolysis, and, most transformatively, hydrogen and oxygen that can serve as rocket propellant. The concept is called in situ resource utilization, and it anchors every serious long-term lunar architecture. The ability to manufacture propellant on the Moon rather than launching it from Earth would fundamentally alter the economics of deep space exploration, converting the Moon from a destination into a supply node. But extracting water ice from permanently shadowed craters at 230 degrees below zero requires an entirely new class of surface operations hardware. Mining equipment must function in perpetual darkness at temperatures that would shatter most conventional engineering materials. Excavated regolith containing ice must be transported to processing facilities where heat is applied to sublimate the ice, converting it directly from solid to vapor, which is then captured, purified, and either stored or further processed into hydrogen and oxygen by electrolysis. Processing installations require substantial power. Storage systems must prevent recovered water and gases from refreezing or venting. Transportation systems must operate reliably across the boundary between illuminated terrain and permanently shadowed regions, crossing temperature differentials of hundreds of degrees within short distances. The decision to concentrate initial Artemis landings at the South Pole is often presented publicly as a scientific preference. The poles are scientifically rich because of their ice deposits and unique geological conditions. This framing, though accurate, understates the architectural compulsion behind the choice. The South Pole is not merely the most scientifically compelling site for sustained human presence. Given current technological constraints, it may be the only viable one. An equatorial outpost positioned like the Apollo landing sites would face the full 14-day lunar night with no sunlight to generate power and temperatures dropping to minus 70 degrees Celsius. Bridging that darkness with current battery technology would demand energy storage systems so massive that launch costs alone would consume a prohibitive fraction of the program budget. Nuclear systems capable of supplying the required power remain under development and are years from flight-ready status at the needed output levels. The south polar peaks resolve this challenge through orbital geometry rather than technological heroics. The Moon's minimal axial tilt means that elevated terrain near the poles can remain in near-continuous sunlight, as the Moon orbits the Sun, receiving illumination for roughly 90% of the lunar year at the most favorable elevations. This converts power generation from an unsolved architectural crisis into a manageable engineering problem. Solar arrays on polar high ground can sustain operations with modest battery reserves for brief shadow intervals, rather than the enormous storage systems that equatorial deployment would necessitate. None of this technology currently exists as flight-qualified hardware. Individual components have been prototyped and tested in laboratory settings and simulated lunar environments. Robotic precursor missions planned under NASA's Commercial Lunar Payload Services program aim to characterize ice deposits and evaluate extraction concepts. But the gap between laboratory demonstration and operational resource extraction at the scale required to support a permanent surface outpost remains vast. Closing that gap will require years of iterative development, field testing, and system integration across many mission cycles. Lunar regolith itself presents a hazard that Apollo encountered but never had to manage over extended operational timescales. The lunar surface is blanketed with a layer of fine, angular particles produced by billions of years of micrometeorite bombardment. Unlike terrestrial sand, which is gradually rounded and smoothed by wind and water, lunar regolith particles are jagged mineral and glass shards with unblunted edges that never erode. These particles accumulate persistent electrostatic charges generated by solar ultraviolet radiation and the solar wind, causing them to adhere tenaciously to virtually every surface they contact. Apollo astronauts encountered significant dust problems even after brief surface excursions. Regolith infiltrated suit joints and degraded mobility. It abraded helmet visors, impairing visibility. It coated optical surfaces and thermal management components. When brought into the lunar module cabin on suits and equipment, it irritated eyes and respiratory passages. Harrison Schmitt, the geologist, on Apollo 17 reported symptoms resembling hay fever following exposure to cabin dust, including persistent congestion and irritation lasting many hours. For 3-day missions, these were tolerable nuisances. For extended operations, they become serious engineering and occupational health concerns. Abrasive regolith particles accelerate wear on mechanical seals, bearings, and moving parts. Dust accumulating on solar arrays degrades power output. Contamination of life support filters and fluid handling equipment degrades system performance and increases maintenance demands. Long-term inhalation of fine regolith particles, which contain a substantial fraction of nanoscale silicate shards, poses respiratory health risks that some investigators have compared to the hazards associated with terrestrial silicosis and asbestosis. Managing dust contamination through extended surface operations requires systems Apollo never carried and never required. Airlock designs that minimize regolith transfer between the exterior and habitat interior. Suit cleaning or suit port systems enabling astronauts to enter and exit pressure suits without bringing them inside the pressurized volume. Dust-resistant coatings and materials for exposed hardware. Cabin air filtration systems capable of removing fine particles continuously across months of operation. Crew respiratory health monitoring protocols. Each item represents an engineering requirement that must be solved, tested, and integrated before extended surface operations can be conducted safely. The aggregate effect of all these demands, closed-loop life support, radiation shielding, thermal management across the full day-night cycle, continuous power supply, in situ resource utilization, and dust control, transforms the engineering challenge into something essentially unrecognizable when compared to what Apollo faced. Apollo needed a vehicle capable of keeping 2 people alive for 3 days in a thermally moderate window, with no resource extraction requirement, minimal radiation concern, and expendable systems throughout. Modern lunar programs need a surface architecture capable of keeping 4 or more people alive and scientifically productive for weeks to months across extreme thermal cycles, with closed-loop environmental systems, robust radiation shielding, independent power generation, and the initial stages of local resource production. This is not a comparison of degree. It is a comparison of kind. Asking why Artemis takes longer than Apollo is like asking why constructing a year-round Antarctic research station takes longer than a weekend camping expedition to the same continent. The location is identical. Everything about the undertaking is different. This is also why the Artemis architecture looks so different from Apollo's comparatively compact 3-vehicle configuration. Artemis involves the Space Launch System for heavy lift from Earth, the Orion capsule for crew transit to and from lunar vicinity, the Gateway, a small space station in lunar orbit, as a staging and logistics hub, a human landing system developed commercially by SpaceX and separately by Blue Origin for crew transport between lunar orbit and the surface. Surface habitats, power systems, rovers, and eventually resource extraction installations. Communication relay satellites providing continuous surface-to-Earth connectivity. Robotic precursor missions to characterize landing sites and test critical technologies. Each element addresses a genuine requirement that Apollo either never confronted or deliberately set aside. The Gateway provides a persistent logistics platform in lunar orbit, supporting multiple landing missions without requiring a full Earth-to-Moon transit for every crew rotation. The commercial landing systems introduce competitive development and cost-sharing arrangements. The surface systems, habitats, power, and rovers enable the extended stays that Apollo's architecture was never designed to support. The human landing system merits a particular examination because it represents the largest single source of both transformative potential and program risk in the entire Artemis architecture. SpaceX's Starship, selected as the landing vehicle for initial Artemis crewed surface missions, is a vehicle bearing almost no resemblance to the Apollo lunar module it nominally replaces. The lunar module stood approximately 6.5 meters tall, with landing gear deployed, and weighed roughly 15 metric tons fueled. Starship stands approximately 50 meters tall and weighs over 100 metric tons empty. The scale difference is not incremental, it is an order of magnitude. This scale enables capabilities Apollo could never have envisioned. Starship's payload volume could transport habitation equipment, scientific instruments, rovers, and supplies sufficient to support surface durations measured in weeks rather than days. Its cargo capacity transforms the logistics of lunar surface operations from the backpacking model of Apollo, where every gram was budgeted with agonizing care, to something closer to an actual expedition with meaningful infrastructure delivered per landing. But this scale introduces a dependency with no precedent in the history of human spaceflight: orbital propellant transfer. Starship cannot reach the lunar surface from a single Earth launch. The vehicle must first attain low Earth orbit and then receive multiple cryogenic propellant deliveries from tanker variants of the same vehicle launched on separate flights. Current projections suggest each lunar mission may require somewhere between 6 and 16 tanker flights to fully fuel a single lunar starship, depending on final vehicle performance and propellant boil-off rates during fueling operations. Orbital transfer of cryogenic propellants, supercooled liquid oxygen, and liquid methane has never been executed at this scale. Technical challenges include managing propellant boil-off in the thermal environment of low Earth orbit, achieving reliable fluid transfer between vehicles in microgravity, maintaining propellant quality across multiple sequential transfers, and coordinating a rapid sequence of tanker flights within a window constrained by orbital mechanics and accumulating boil-off. Each challenge is resolvable in principle. None has been validated in practice at operational scale. The Artemis architecture is more complex than Apollo not because its designers were less creative, but because the problem being solved is more complex. You cannot establish a permanent surface outpost with a 3-vehicle stack optimized for a 72-hour visit. The added complexity is not bureaucratic overhead. It is engineering necessity. The timeline implications are substantial. Apollo progressed from Kennedy's speech to a lunar landing in 8 years, a pace enabled by unlimited budgets, wartime urgency, and extraordinary risk tolerance. Artemis, operating under constrained budgets, modern safety standards, and the need to develop technologies Apollo never attempted, will require more time. Not because today's engineers are less capable. Contemporary aerospace engineers work with tools and knowledge their Apollo predecessors could not have imagined. But because the problem they are solving is categorically more demanding. The temptation to compare timelines directly, to ask why we cannot replicate in 8 years what Apollo accomplished in 8 years, ignores everything that has changed about mission objectives, safety standards, budget realities, and the industrial base. It compares a sprint to a construction project. Sprints are faster. Construction projects produce something that endures. What Artemis is pursuing has no genuine historical precedent. Apollo was a magnificent achievement with recognizable parallels in other concentrated mobilization efforts. The Manhattan Project, wartime industrial conversion. Sustained lunar presence has no parallel. No nation has ever established permanent habitation on any body other than Earth. The International Space Station is the closest analog, but it occupies the comparatively forgiving environment of low Earth orbit with regular resupply access and the option of emergency crew return within hours. The Moon offers none of those conditions. It is 3 days from Earth. Resupply requires dedicated missions planned months in advance. Emergency return requires a functioning ascent vehicle, awaiting orbital spacecraft, and a transit duration that makes rapid medical intervention impossible. Every system must perform, or the crew must be able to sustain themselves until repairs succeed. The margin for error contracts sharply compared to orbital operations, even as the environment becomes substantially more hostile. This is the reality separating modern lunar ambitions from Apollo's achievement. The destination is 384,000 kilometers away, the same distance it has always been. But the journey, measured not in kilometers, but in the complexity of what must be built, tested, qualified, launched, assembled, and maintained, is orders of magnitude greater than anything Apollo attempted. The moon is not harder to reach than it was in 1969. It is harder to inhabit, and habitation is the entire rationale for returning. A seventh set of boot prints in the regolith, however symbolically resonant, would not justify the investment. What justifies the investment is infrastructure that persists. Systems that generate power across the lunar night, extract water from ancient ice, shelter crews from radiation, and transform the moon from a place we briefly visit into a place we genuinely use. Building that infrastructure is the actual objective, and it requires something no engineering achievement can substitute for: sustained institutional commitment across decades, stable funding through political transitions, and the organizational patience to solve problems that do not yield to urgency alone. Whether those conditions can be created and maintained is not an engineering question. It is a political one, and it is the question on which everything else depends. Everything examined so far converges on a single uncomfortable conclusion that most space enthusiasts resist confronting. The principal barrier between humanity and a permanent return to the moon is not technical. It is institutional. Engineers understand how to address the thermal problem, the radiation problem, the life support problem, the dust problem, the power problem. They have proposed credible architectures, built functioning prototypes, and validated subsystem designs through rigorous testing and simulation. The engineering is extraordinarily difficult. But difficulty is the domain engineers inhabit. Given adequate time, stable funding, and coherent direction, they will resolve every technical challenge the moon presents. The question that actually determines whether humans return to the lunar surface and remain there is a different one. It is a question about governance, money, patience, and the particular difficulty democratic societies have sustaining commitments that outlast individual election cycles. It is a question about whether the species that erected the Great Pyramids over generations and raised the medieval cathedrals over centuries can summon the same generational persistence for a project whose returns are measured not in years but in human lifetimes. This is where the story of lunar return becomes fundamentally unlike the story of Apollo. Apollo demanded solving an engineering problem under conditions of extraordinary political necessity. Modern lunar return demands solving a political problem under the conditions of ordinary democratic governance. The second challenge is, in important ways, harder than the first. Begin with the structural mismatch that has defeated every post-Apollo attempt at lunar return, because it is the single most important factor in this entire narrative and the one least examined in popular discussion. Developing a new human-rated deep space transportation system from initial design concept to operational flight takes between 10 and 15 years under favorable conditions. That is not a pessimistic projection. It is the observed historical pattern across multiple programs and multiple nations. The Space Shuttle took approximately 9 years from the program approval to first flight. The International Space Station required over a decade from initial agreement to first module launch. The Space Launch System, built substantially from heritage shuttle hardware, took over 12 years from formal authorization to first flight. The Orion capsule has been in development for nearly 2 decades. These timelines are not products of organizational incompetence or bureaucratic bloat, though both exist in any large institution in varying measure. They reflect the genuine complexity of designing, constructing, testing, and certifying systems that must perform with extraordinary reliability in environments that destroy most human artifacts. Human spaceflight hardware must withstand launch vibration intense enough to disintegrate conventional structures. It must operate in hard vacuum. It must endure thermal swings spanning hundreds of degrees. It must protect crew members against radiation, micrometeorites, and the slow degradation of every seal, bearing, and fluid system across extended operational lives. Certifying that hardware satisfies those requirements entails testing regimes that cannot be meaningfully compressed without accepting risk profiles that contemporary safety standards prohibit. A realistic projection for establishing sustained lunar surface capability. Not a single expedition, but an operational outpost with habitats, power systems, surface transportation, and the beginnings of resource extraction, spans 20 to 30 years from program initiation to mature operations. This is not pessimism. It is a projection grounded in the observed pace of every comparable space infrastructure program in history. Now, set that technical timeline against the political timeline within which it must operate. An American president serves a maximum of 8 years. Congressional terms run 2 years in the House and 6 in the Senate. Federal budgets are authorized and appropriated annually, with limited mechanisms for binding future legislators to multi-year spending commitments. Each new administration arrives carrying its own space policy priorities, its own NASA administrator, its own congressional relationships, and its own political judgment about how to allocate discretionary spending. The arithmetic is relentless. A program requiring 25 years of consistent investment must survive at least 3 and possibly 4 presidential transitions. It must maintain support across 6 or 7 congressional election cycles. It must endure economic contractions, competing national priorities, shifting international conditions, and the inevitable technical setbacks accompanying any complex development effort. It must accomplish this while generating visible progress at a pace sufficient to justify continued investment, yet slow enough to satisfy technical responsibility. Not one post-Apollo lunar program has navigated this successfully. Not a single one. The Space Exploration Initiative of 1989 was functionally dead within 2 years. The Constellation program of 2004 was terminated after 6. Even Artemis, which has survived 1 presidential transition and currently retains bipartisan congressional support, has seen its timeline extend and its architecture revised through successive budget cycles. The pattern is not a collection of individual failures. It is a structural feature of how democratic governance interacts with long-duration engineering programs. Some analysts conclude from this history that sustained lunar presence is politically unachievable, that democratic societies are institutionally incapable of maintaining the multi-decade commitments that permanent space infrastructure requires. That conclusion is understandable but premature, because at least one compelling counterexample demonstrates that democratic governance can sustain complex space programs across multiple administrations when the institutional architecture is correctly designed. The International Space Station has maintained continuous human habitation since November 2000, over 25 years of uninterrupted crewed operations spanning 5 American presidential administrations, numerous congressional elections, and at least 2 major economic crises. The station survived the Columbia disaster and the extended grounding of the shuttle fleet. It survived the complete retirement of the shuttle program, transitioning crew transport to Russian Soyuz vehicles, and then to commercial American spacecraft. It survived geopolitical tensions with Russia that, in other contexts, might have destroyed the partnership entirely. How did the station endure when lunar programs could not? Several factors contributed, and each carries lessons for Artemis and its successors. First, the station created international dependencies that raised the cost of cancellation above what any single partner was willing to pay. When the European Space Agency constructs a module, when the Japan Aerospace Exploration Agency contributes a laboratory, when the Canadian Space Agency provides a robotic arm, canceling the program means not merely absorbing domestic investment losses, but damaging diplomatic relationships with allies whose cooperation is essential across dozens of other policy domains. The station embedded itself in a web of international obligations that no administration could cleanly unravel. Second, the station distributed economic activity across enough congressional districts to generate a domestic political constituency for its continuation. Components were manufactured across many states. Operations were directed from facilities in Texas, Alabama, Florida, and elsewhere. Contracts sustained thousands of jobs in communities where aerospace employment represented a substantial share of the local economy. Canceling the station meant eliminating those jobs, a political cost that office holders in affected districts were unwilling to absorb regardless of their party. Third, the station produced continuous visible output. Crews launched and arrived on schedule. Scientific experiments generated publications and public interest. Astronauts developed public profiles connecting the program to ordinary citizens through social media, educational programming, and live broadcasts from orbit. The station was never absent from public view long enough for its existence to feel abstract or expendable. Artemis has begun adopting comparable structural strategies, and this represents one of the most consequential but least publicized differences between the current program and its predecessors. The Artemis Accords, signed by over 40 nations at last count, establish a shared framework of principles for lunar exploration. These agreements are not binding treaties in the formal legal sense, but they generate diplomatic expectations and institutional relationships that increase the political cost of American withdrawal. When Australia, Japan, the United Kingdom, Italy, and dozens of other nations sign onto a cooperative framework for lunar exploration, the United States cannot easily exit without consequences extending well beyond space policy. More concretely, international partners are contributing critical hardware. The European Space Agency builds the service module for the Orion capsule, the segment providing propulsion, electrical power, and environmental control during transit. This is not a ceremonial gesture. It is a critical path contribution without which Orion cannot operate. Japan is developing a pressurized lunar rover intended to allow astronauts to traverse the surface without wearing pressure suits, dramatically extending operational range. Canada is contributing robotic systems for the Gateway. Each contribution establishes a mutual dependency binding partner nations to the program and making unilateral American cancellation diplomatically prohibitive. Commercial partnerships likely represent the most structurally significant innovation in Artemis relative to all previous lunar programs. Understanding why requires appreciating how completely the commercial space industry has been transformed since the most recent serious attempt at lunar return. When Constellation was canceled in 2010, the commercial space sector was still establishing its credibility. SpaceX had successfully flown its Falcon 1 rocket only twice. Blue Origin had not yet flown any orbital vehicle. The proposition that private companies could develop, build, and operate human-rated spacecraft at costs substantially below traditional government programs was promising but unvalidated. Today, the landscape is unrecognizable. SpaceX routinely launches orbital-class rocket boosters and recovers them for reuse, a capability widely considered technically implausible by mainstream experts as recently as 2012. The company's Falcon 9 has become the most frequently flown orbital rocket on Earth. Its Crew Dragon spacecraft has transported dozens of astronauts to the International Space Station under NASA contract at per-seat costs roughly 1/4 of what shuttle flights required. The company's Starship vehicle, currently in active developmental testing, is designed to be the largest and most capable fully reusable launch system ever constructed. Blue Origin, while at an earlier stage of operational development, is advancing the New Glenn heavy-lift rocket and has been selected to develop a second human landing system for later Artemis missions. Rocket Lab, Relativity Space, and numerous other companies are expanding the industrial base for launch vehicles and spacecraft components. The commercial space ecosystem now encompasses dozens of entities capable of contributing to lunar exploration across various layers of the supply chain. This depth of commercial capability matters for program resilience in ways that are easy to underestimate. When SpaceX develops the Starship human landing system for Artemis, it does so under a contract structure in which NASA pays milestone-based fees, while SpaceX invests substantial private capital in the underlying vehicle. Starship is not being built for NASA alone. It is being developed as a general-purpose transportation platform with commercial satellite deployment, Earth point-to-point transport, and private spaceflight applications. The lunar landing mission is one use case among many for a vehicle with broad commercial purpose. This means that even if NASA's specific lunar program were disrupted by a budget reduction or a change in administration, the underlying vehicle development would likely continue independently. SpaceX has commercial motivation to complete Starship regardless of government lunar policy. The technological foundation for lunar surface access becomes partially decoupled from the political cycles that have destroyed every previous lunar program. That decoupling is genuinely novel. It did not exist during Constellation. It barely existed in Artemis's early years. It represents a structural resilience that government-exclusive programs cannot replicate. The same reasoning applies to other commercial participants. Companies developing lunar surface rovers, power systems, communication relays, and resource prospecting equipment under NASA contracts are constructing capabilities with applications extending beyond any specific government program. Lunar surface access has begun attracting private investment from the parties interested in resource extraction, tourism, scientific services, and communications infrastructure. These commercial interests generate constituencies for lunar development that exist independently of any individual government program's survival. None of this ensures success. Commercial partnerships introduce their own complexities, schedule uncertainty, technical risks, and the possibility that key companies might face financial difficulty or shift strategic direction in ways that defer critical program elements. Starship's development timeline has proven difficult to forecast accurately, and the gap between prototype testing and crew-certified operational flight remains considerable. But the structural advantage of a distributed commercial foundation compared to the single contractor government program model of earlier eras is substantial and historically without precedent. Budget scale remains the most persistent constraint, and candor requires acknowledging that modern lunar programs operate at resource levels far below what Apollo commanded. NASA's annual exploration systems budget has grown in recent years, but still represents a small fraction of Apollo-era investment measured as a share of federal spending. This means that capabilities Apollo developed over years will require a decade or more for Artemis to match. The pace differential is not primarily a reflection of engineering difficulty. It is a reflection of funding levels. Some analysts contend that commercial efficiencies and modern technology can close this gap. There is partial evidence for that position. SpaceX has demonstrated that iterative development with high flight cadences can produce capabilities at substantially lower cost than traditional approaches. The company's methodology: build hardware rapidly, test aggressively, treat failures as data, iterate quickly, compresses development timelines in ways that traditional programs emphasizing exhaustive pre-flight analysis and risk minimization cannot match. But iterative development at that tempo generates tensions with human spaceflight requirements that have not yet been fully resolved. Starship prototypes have experienced dramatic failures during testing. Catastrophic vehicle losses, control failures, landing mishaps. Each is an expected and accepted element of the development process within SpaceX's engineering culture. Each also generates media attention and public scrutiny that could, under different political conditions, erode congressional support for the program. Managing the dynamic between aggressive commercial development and the public confidence necessary for sustained political backing is an ongoing challenge with no clear historical precedent. The geopolitical dimension of contemporary lunar return merits careful examination because it presents both opportunity and risk in roughly equal measure. China's space program has achieved substantial milestones across the past decade. The Chang'e missions have successfully landed robotic spacecraft on the lunar surface, including the first-ever landing on the lunar far side with Chang'e 4 in 2019. Chang'e 5 returned lunar samples to Earth in 2020. China has announced its intent for crewed lunar landing by approximately 2030 and has partnered with Russia to develop the International Lunar Research Station, a permanent surface facility intended to begin construction in the late 2020s and early 2030s. These ambitions have concentrated attention among Western policymakers on the strategic importance of maintaining leadership in cislunar space. Congressional support for Artemis has been reinforced by the explicit recognition that the United States faces a credible competitor beyond low Earth orbit for the first time since the Soviet era. This competitive dynamic provides political motivation for sustained investment that purely scientific or economic arguments have historically proven insufficient to generate. But competition also carries the risk of replicating Apollo's central structural failure. If lunar return becomes framed primarily as a race against China, a contest to claim presence and prestige before a rival arrives, the resulting program could prioritize velocity over durability, spectacle over infrastructure, and political timelines over engineering realities. A crash program designed to reach the South Pole before China in 2028 would face precisely the pressures that made Apollo spectacular and unsustainable. Compressed schedules, elevated risk tolerance, and an architecture shaped by a single demonstration rather than enduring capability. The most constructive outcome would be competition that motivates investment, while program architecture ensures resulting capabilities serve long-term objectives rather than short-term optics. This demands political leaders capable of distinguishing between a race and a construction project. Leaders willing to accept that arriving at the moon somewhat later with infrastructure designed for permanence is strategically superior to arriving first with a program that exhausts itself in the attempt. The legal framework for sustained lunar presence raises dimensions Apollo never encountered, and that remain incompletely resolved. The Outer Space Treaty of 1967, ratified by all major spacefaring nations, prohibits national sovereignty claims over celestial bodies. No nation can plant a flag on the moon and assert territorial dominion over surrounding terrain. This principle enjoys broad acceptance and is unlikely to be challenged directly. But the treaty does not explicitly govern the extraction and commercial use of lunar resources. If a nation or company excavates water ice from a permanently shadowed crater and processes it into rocket propellant, does that constitute impermissible appropriation of a celestial body? Or is it analogous to fishing in international waters, extracting resources from a shared global commons without asserting sovereignty over that commons? The Artemis Accords attempt to establish norms around this ambiguity, affirming that resource extraction is compatible with the Outer Space Treaty and encouraging transparency and avoidance of operational conflicts in the selection and use of activity zones. But not every spacefaring nation has endorsed the accords. China and Russia have declined to sign, and their planned International Lunar Research Station operates within a separate bilateral framework. The potential for competing legal interpretations and overlapping operational footprints in resource-rich polar terrain introduces geopolitical complexity, requiring diplomatic management extending well beyond any single space program's mandate. Where does all of this leave us? What is the honest assessment of where humanity actually stands in its effort to return permanently to the moon? The engineering challenges are genuine but addressable. Closed-loop life support, radiation protection, thermal management, surface power, in situ resource utilization, and dust control are all problems with identified solution pathways. None demands a breakthrough in fundamental science. All require sustained investment in development, testing, and operational qualification. The industrial base is reconstituting itself. Not from the ruins of Apollo, that capability is irretrievably lost, but on a new foundation of commercial space enterprises, international partnerships, and contemporary manufacturing methods. This new foundation is in several respects more resilient than Apollo's because it is distributed across multiple independent organizations, each with its own motivations for continued investment in the underlying technology. Political alignment is more favorable than at any point since 1972. Bipartisan congressional support for Artemis, active international participation, robust commercial engagement, and competitive pressure from China combine to produce a constellation of motivating factors that no previous post-Apollo program has benefited from simultaneously. This combination does not guarantee survival through future political transitions, but it measurably improves the odds relative to programs that depended exclusively on a single administration's enthusiasm. The timeline will be long. Not Apollo long, not 8 years from announcement to a first landing, but decades from program initiation to mature, sustainable surface operations. The first Artemis landing, whenever it occurs, will not represent the culmination of the endeavor. It will mark the beginning. The years and decades following that initial landing will determine whether it becomes another Apollo, a magnificent dead end, or the opening chapter of something genuinely permanent. Success demands a form of commitment democratic societies find genuinely uncomfortable. It requires committing today to expenditures whose benefits will materialize during the terms of future leaders not yet in office. It requires accepting that the program will not conclude before the next election, or the one after, or possibly the one after that. It requires absorbing setbacks, schedule expansions, and cost increases without abandoning the objective. It requires sustaining institutional coherence across the personnel changes, budget pressures, and shifting priorities that characterize democratic governance over multi-decade spans. Humanity has demonstrated this capacity before, though rarely and never without difficulty. The great infrastructure achievements of the 19th and 20th centuries, transcontinental railways, the Panama Canal, the interstate highway system, each required decades of sustained investment through political transitions, economic disruptions, and vigorous public controversy. They succeeded not because every participant agreed on every decision, but because a sufficiently broad coalition recognized the long-term value of the undertaking and defended it through the inevitable difficulties. The moon requires that same quality of commitment. Not the frantic urgency of Apollo, which burned intensely for a decade and extinguished itself the moment its political purpose was served, but something steadier and less dramatic and ultimately more durable. The slow, unglamorous, budget-constrained work of building infrastructure designed to outlast the people who authorize and fund it. We did not fail to return to the moon because the goal proved impossible. We did not return because the extraordinary conditions enabling Apollo, the existential geopolitical threat, the unconstrained funding, the tolerance for mortal risk, the focused national purpose, dissolved the moment the political objective was fulfilled. What followed was not failure. It was normality. And normality, as it turns out, is a far less accommodating environment for extraordinary things. The conditions enabling a permanent return are now assembling. Not ideally, not swiftly, not without frustration and setback and the persistent risk that political cycles will again disrupt what engineering has begun. But the trajectory is, for the first time in half a century, genuinely and credibly aimed at the lunar surface. Not driven by crisis, not propelled by a race, but because enough people across enough institutions and enough nations have committed to the difficult, methodical work of building something designed to last. The moon is 3 days distant. It has always been 3 days distant. The remaining distance is not measured in kilometers. It is measured in political will to sustain funding across administrations, in industrial resolve to develop hardware across decades, in international cooperation sufficient to distribute costs and risks across many partners, and in institutional patience to absorb failures without losing the thread of the objective. That distance is closing. Imperfectly, slowly, with the uneven and often frustrating rhythm that marks every ambitious undertaking in a democratic society. But it is closing. The 12 astronauts who walked on the moon did so under conditions that will not come again. They were the product of a singular historical moment, a convergence of fear and ambition and political will condensed into the most remarkable engineering sprint in the annals of human civilization. What they accomplished was not the opening of an era. It was the summit of a crisis. What follows, if it follows, will look nothing like Apollo. It will unfold more slowly, with greater complexity, with broader international involvement, and with deeper commercial roots. It will not generate the same condensed sense of sudden triumph. There will be no single moment when a civilization collectively holds its breath watching a blurred broadcast of footprints being pressed into alien dust for the first time. Instead, there will be the gradual and largely invisible accumulation of capability. A habitat deployed and pressurized, a power system brought online, a water extraction demonstration run successfully, a crew rotation completed, another and another and another, until a human presence on the lunar surface is no longer a notable event, but an unremarkable fact. That is the process by which civilizations construct things that endure, not in concentrated bursts, but through sustained effort, not through the crucible of crisis, but through the quieter discipline of commitment. The moon waits as it has always waited, patient, silent, indifferent to human schedules and political rhythms. It will be present whenever we arrive with the capability and determination to stay. The question was never whether we could return. The question has always been whether we can build the kind of civilization that sees its commitments through to completion. That question remains unanswered. The answer does not hinge on propulsion systems or habitat modules or resource extraction technology. It rests with us, and with whether we possess what may be the most scarce and undervalued of human capacities. Not the courage that flares in moments of danger, but the steadiness that persists across the long, unobserved years when the work is hard and the destination is not yet visible. Apollo demonstrated that we can be bold when the stakes are existential. The 5 decades that followed demonstrated that boldness without continuity is not sufficient. What the moon now requires is something more difficult to summon than a single heroic effort. It requires the resolve to keep going. And whether humanity can sustain that resolve across decades and administrations and the endless competing demands of democratic life is the question that will determine everything that follows. The moon has always been within reach. We are the ones who must decide, again and again, to keep reaching for it.